Okay, and welcome to the final video where we look at using logarithms to help us deal with nonlinear data. It's a very powerful technique, and you'll see this again in statistics in year 2. So let's begin the final video. So, what is the point of using logs with nonlinear data? Well, imagine we had, let's say I had 2 graphs, and I put some raw data. And when I put the raw data, I could see a pattern emerging. And the pattern could be a exponential equation, it could be a polynomial equation. Okay, we don't know. But if we use logarithms to straighten that curve into a line and then manipulate that equation, it is possible to find an equation which can fit as many points on the raw data as possible. Okay, so the aim of all this is to try and find an equation which can hit as many of these points in the original graph or the original data set. Okay, so if I sort of have a look at this, a lot of what we're looking at is nonlinear data. So if we collect some data and does not follow a linear relationship, logarithms can be used to manage these nonlinear trends. And these are the 2 types that you may have to deal with. The first type is what we call polynomial. So we could get raw data that follows an x squared graph. It could be data that follows an x cubed graph, etc. Anything like that, x to the power of any number. The second type is where we've got exponential, where the x is the power, okay? And the equation could look anything like, I don't know, 1 times 2 to the power of x, or 3 times a half to the power of x. Okay, it could be anything in that sort of format. And our job is to try and get these unknowns. So in the polynomial case, we're trying to get the unknown value of a and n, and the exponential case, we're trying to get the unknown value of a and b. Okay, how we get that depends on us being able to look at the data and transform it. Okay, so what we've got to do is think about how we can break down these 2 types. So if I have the polynomial form, how can I break that down into a linear form? Well, if we apply logs on both sides, we can eventually get to this line here. And when we get to this line here, we can compare it to y equals mx plus c. By logging both sides, what we're doing is we're forcing the data points to become linear in nature. And when we force the data points to become linear in nature, then we can then get the value of a and n. So what we're going to try and get is a graph where we've got log y against log x. Okay, so that will be the situation here. And in case 2, if we apply logs again on both sides here and simplify, you get to this stage, we're going to get a graph of log y against just x. Once we've drawn these 2 types of graphs, depending on the situation, we will then get linear data as close to linear as possible. Okay, and once we get that data, we can find out, the first thing we can find out is the y-intercept, and next thing we can find out is the gradient. And by finding out those 2 bits of information, we can then get the unknown values, which will either determine polynomial or exponential. So let's have a go at an example. So the key points that we need to understand is which log form are we using for which type. Are we looking for a polynomial or exponential? And then having a go at plotting. So we've got this data here. This is some raw data. and it's believed that the variables are connected by this formula. Now what we've got to do is analyse that and think, is that polynomial exponential? Now exponential, you'd expect to see x as the power, so this is polynomial. Okay, so we need to find the value of a and n. It's believed that the variables are connected by that formula, therefore part A, plot a graph of log v against log x. So for part A, log v against log x, so I'm going to have log x here and log v here. And all I need to do is use my calculator, so I'm going to shift this calculator, this button here, that will give me log because it's to the base 10. I'm going to find log of all the x values, log 0.5 minus 0.30 log 1, which is 0, log 1.5, which is 0.18, log 2, which is 0.30, log 2 log 3, so log 4, which is 0.60, and log 5. Which is 0.70. Okay, so I've done log x, so I basically applied log on all these x values. Now I'm going to do the same with log v, log 2.6, 0.41, log 20, 1.30, log 71, 1.85, log 170, 2.23, log 1350, 3.13, log 2600, 3.41. So I've done that. I'm going to plot a graph of log v against log x. So obviously log v will be on the y, log x will be on the x. It's going to plot this, so minus 0.3 and then 0.41, so it's going up in 0.2. Roughly there. 0, 1.3, 0.18, 1.85, 0.3, 2.23, 0.6, 3.13, and 0.7, 3.41. Okay, so I've plotted the graph. Now I'm going to find a line of best fit through these points. Okay. Part B, use a graph to find the values of a and n. So let's just break this down. This is the polynomial form. Now if we look at the notes, top, I'm just going to do this a bit manually, so I'm going to show you how we can get a straight line equation. If I log both sides, use multiplication law, I'll get to this stage here. Now once I got to this stage, you've got to think, okay, this is my y, this is my m, this is my x, this is my c. Yeah, the x-axis is log x, the y-axis is log y, and then you have to figure out what a and n are. That's question B. So a, that comes from the fact that log a is equal to the y-intercept, and the y-intercept is clearly 1.3, and the gradient m gives us the value of n, so we need to find the gradient. Now let's look at part A. Log a equals 1.3, log base 10 to the power of a equals 1.3. That means that a equals 10 to the power 1.3. Which is 19.95. Okay, and n is the gradient. So if n is the gradient, I need to find, how do I find the gradient of a straight line like this? You can pick two coordinates, so y2 minus y1. Let me take these two coordinates here, 1.3 minus 0.41, and then the change in x, 0 minus 0.3. You get a gradient value of 2.96, recurring 2.97 to 2 decimal places. Okay, so that means originally the graph had the equation v equals a, which is 19.95, times by x to the power of 2.97. Okay, now let's see if that's a good enough fit for the data that we have. So if I do 19.95 and I'll multiply by 1 to the power of 2.97, okay, I should be able to get a v value of roughly 20, which is not too far off. Let's see if I can get close to 71. So I'm going to do 19.95 times by 1.5 to the power of 2.97. I should get close to 71. I've got 66.51. That's not too bad. Now I've got my equation, v equals 19.95x to the power of 2.97. Find the value of v when x equals 3. So I'm going to solve x equals 3, and therefore v equals 19.95 times by 3 to the power of 2.97. I should get 521.2 as my answer. Okay, so let's just recap this again. They've told us that it's in this form, a polynomial form. If it's in a polynomial form, based on case 1 here, I'm going to have to get the y-intercept and the gradient in order to get a and n. So once we figure that out, I then need to draw a graph of log x against log y, in this case is log v. So I'll plot the values log x against log v on a table. I then plot the graph. I find the gradient and I find the y-intercept of this line, and I use mathematics to get the unknown values of a and n. So this is the polynomial example. The next example on the other page will deal with an exponential. Okay, so question 2. Okay. It's believed that these variables are related by the formula m equals ab to the t. Clearly this is exponential form because that's our variable x and this is variable y. By drawing a graph of t against log m, find the values a and b to two significant figures. Right, so we need to find t and log m. So I'm just going to add another column. I'm just going to log all these m values. Two point two, 2.1, 2.0, 1.8, 1.6, and 1.3. Okay, now I've done that, I'm now going to plot the graph of t against log m. So t will be on the x-axis, log m is here. So when t is 1, log m is 2.2. When t is 2, log m is 2.1. When t is 3, log m is 2. When t is 5, log m is 1.8. When t is 7, log m is 1.6. And when t is 10, it's 1.3. Okay, so I've drawn the graph of t against log m. Now I just need to do a line of best fit through them. Okay. So let's just think about the reasoning behind this. Remember, we want an exponential form here. So if I apply logs, the graph is being linearized. So if I apply logs, log m equals log ab to the t. I'm going to get log a plus t log b, which is y equals c plus mx or xm. Yeah, because t is the x-axis, log m is the y-axis. So the gradient is log b, and the y-intercept is c. So I need to find gradient and y-intercept. Now the y-intercept, if I read this off, 2.2, 2.4, is 2.4. So log base 10 a is equal to 2.4. A is equal to 10 to the power 2.4. If I find the gradient, which you can use the table, okay, so changing y, so you've got 2.1 minus 2.2 over 2 minus 1, just use a table really, that's minus 0.1, that's the gradient, but remember the gradient's actually equal to log b, therefore b is equal to 10 to the power minus 0.1. So 10 to the power of 2.4 is 251.188, but we want two significant figures, so it's 250 and 10 to the power of minus 0.1. Again, two significant figures, 0.79. So I found A and B by using the skills with logs, and then part B, therefore find the value of M at the start and end of the experiment. Well, let's have a look at what the equation will look like. M equals AB to the T. A is 250 times by B, which is 0.79 to the power of T. Okay, and we want it at the start of the experiment. So at the start of the experiment, when T equals 0, you literally put in T equals 0. 250 times 0.79 to the power of 0, you get 250. And at the end of the experiment, when T is equal to 10, 250 times 0.79 to the power of 10, you should get M equals 23.67 or 23.7. Right, so that's the end of logarithms. We've looked at all the different types of skills, and we finished off with nonlinear data, where again we reiterate we're going to have some raw data which needs to be linearized using logs, and in all cases you need to find the gradient and the y-intercept in order to find unknown values, either in polynomial form or exponential form. Okay, so that's the end of the video, and that's the end of logs in year 1.